Welcome to the Internet of Things equation, a podcast when I talk about the Internet of Things domain both from the technical and business perspectives. I'm Łukasz Malinowski, the Internet of Things advisor and trainer. My today's guest is experienced executive focused on sophisticated products including satellites, nanosats, and biophysics instrumentation. Today, we will cover the topic of leveraging Internet of Things technology for Chromecasting from space. Hello, Dan. Thank you so much for accepting my invitation.
Hi, Lucas. Thank you.
Could you briefly introduce yourself to the listeners?
Well, I'm Dan Harkins, and I am the COO of Tropical Weather Analytics, Inc., and our mission is to develop Hurricane Hunter satellites, which the first two will launch late 2025 or early 2026. And these satellites will provide earlier and more accurate hurricane forecasts, but also collect wind and cloud data that will improve all weather forecasts across the globe.
Could you give us some history of the tropical weather analytics? Is that your focus always from the space-based forecasting, or that's something that you added?
Actually, the mission history is pretty interesting. It goes quite a while back, over 20 years ago. This originally started as a joint project between the US and Russia. Just after the fall of communism, they were looking for ways to work together and improve relationships. And they came up with something called Project Ramos, which was going to be two weather satellites. We would make one, they would make the other one. The satellites work in tandem together to collect 3D wind and cloud features. Basically, it's a stereoscopic effect. They're looking at the same feature from opposite angles, and then those images are stitched together. Sadly, that mission got canceled before the satellites were made, but from there, NASA and DoD wanted to continue funding the technology, so they took that up with a company called Visidyne, which actually Visidyne was involved initially in the first place. Visidyne then became Tropical Weather Analytics when we decided to commercialize a few years ago, and so we spun off into that. So after many years, we finally got onto the space station over 5 years to test and validate the measurement technique. And lucky us too is that some of the other satellites that went up had some of the measurements that were difficult to get, which we can now get for free from them. And this made these satellites much more cost effective and much smaller than they would have been. So this has allowed us to kind of commercialize the weather forecast that we can develop.
What makes space technology so interesting when forecasting and tracking extreme weather events like hurricanes? Because we use just Earth-based technology and sensors, or space provide some unique advantages?
There's plenty of unique advantages. One of the first ones is that the US is the only country with Hurricane Hunter aircraft. These are aircraft that fly right into the storms and drop sondes and take measurements. Those are really extremely useful for the US, but hurricanes happen across the globe, not just in the US. We bring similar capability to countries that just do not have that kind of infrastructure in place. Even above what the hurricane hunters can do for the aircraft is that we take a specific measurement of cloud top heights and model hurricanes in a different way. Without that cloud altitude measurement, you just can't use this better model that meteorologists pretty much know exists. There's basically used today is something called the Dvorak method or the advanced Dvorak. We'll be modeling as a Carnot engine, and that can reduce the uncertainty by as much as 2 and 3 times. So that actually gives us an earlier and more accurate track of the storm and its intensity.
You mentioned taking measurements. Could you give us some hints regarding the sensors? IoT is all about sensors that gather data from physical world and then transfer that data into digital representation. So what sensors are used by those satellites to track hurricanes?
Yeah, oddly enough, we don't use sensors per se. We use cameras that visibly look at cloud motion. And by looking at it in 3D, we can then derive not just you get a nice image that looks good in 3D, but you can actually derive from the movement the wind across all altitudes. Because as we see these features move, we understand against background and everything else. So it's really about the algorithms and the processing more than sensors. Although what will play a large part in when we are integrating our 3D wind data. So basically, we get these images and then we turn them into a 3D point cloud of wind velocities. And eventually, these wind velocities of any cloud feature, it's not just hurricanes, these will be integrated with other terrestrial and satellite data by weather forecasters. So IoT will play a huge role in that because a lot of independent weather stations, as well as even the small weather stations, are all feeding into the models that the meteorologists are using. So the more stations that are had on the ground, the more that we can validate what we're measuring from space, and on and on. It just improves the forecast. The more sensors, the better, I guess, for sure. And the more observation techniques that we can all stitch together, the better the forecast we can provide. And IoT especially can be a cost effective way in remote places. If you have a smaller weather station where we can combine our coverage with some of these smaller forecasting stations in places where they can't simply afford or don't have the resources for weather radars stations. So these small stations, and then combined with our data, could really help provide forecast to places that just they simply don't have it. And while we think that weather's free and it's global, it's universal, the satellites take care of all that. It's really hyper-local forecasts are extremely important, especially as climate change is becoming more and more of an issue. So the people that are hit hardest almost don't have the infrastructure to actually have these hyper-local forecasts. So that's where we'll be stepping in to kind of alleviate a lot of that and bring coverage to where it is not existing at the moment.
You mentioned one of the core value propositions of IoT, which is ecosystem, and that you can combine data from various sources like stations, satellites, and fit all of that into algorithms to provide those weather forecasts. On your site, I read that you provide 4D measurements. Could you explain the concept of 4D measurements?
Yeah, it's basically the three dimensions in the XYZ axis and plus time. So that time aspect is actually a big deal. We always talk about 4D, but it kind of confuses people sometimes when we say four dimensions. We say 3D, 4D interchangeably all the time. That time element, obviously, especially when it comes to weather, and that we're deriving cloud motions based on time. So that really becomes a big deal. And at the moment, 3D wind data is extremely hard to get. There's not a lot of it across all altitudes. And what there is available is only at the 1 kilometer scale. Whereas when our satellites are up, we'll be able to provide at 100-meter scale. So that's 10 times factor that we'll be improving 3D wind.
Are we talking about real-time data? I believe that hurricanes are extremely hard to predict, and you need to have real-time insights in order to track them and to get a good accuracy of predicting where they are heading. Can your solution provide real-time data, or is that some batch data that is processed and you've got results after some time?
Yeah, so this will definitely be near real time that we will be processing data. Our goal eventually will be 15 minutes from any event observation once we have enough satellites. So from 15 minutes that we'll be able to observe and apply the data and actually have not necessarily a forecast, but we will be able to get that information into a forecaster's hands so that they can run it into their model. But we do expect that every 2 hours that we'll be able to deliver an updated forecast based on the amount of satellites we have planned now, which the initial constellation will be 10 satellites.
You mentioned the Hurricane Hunter satellites. How does they differ from satellites that are already in the orbit?
So the only satellites that are focused on measuring the clouds and the wind at a resolution and revisit rate that we can provide, as well as, again, 3D is extremely difficult to come by. There haven't been many satellites that can actually measure that. It's kind of been the holy grail of weather observation for quite some years. And geosats don't provide full globe. They do cover the globe, but not at the resolution rate that we can provide. And then there's no LEOsats at the moment that are collecting this type of information either. The way we model hurricanes is unique and different than what other satellites can provide. And the wind data and cloud data at the 100-meter resolution, 1 meter per second for wind, plus or minus accuracy. Those features are the unique aspects that we can't get from other satellites at the moment.
If you could give us a bit more details around that, because you mentioned that use high resolution camera. This is essentially a sensor that takes a picture of Earth, and based on the frames, so subsequent pictures, you can calculate movement of wind and clouds. Is that correct, or is it way more advanced, or maybe you use different spectrums to measure different attributes?
It would actually just be visible light for the moment, but in generation 2, we will want to do nighttime. So at the moment, we are limited to just visible clouds. So we're just looking, the cameras have a very wide field of view. Most people are looking to either get what's beneath the clouds to look at. Most satellites want to see what's on Earth, not necessarily the clouds. And they also want really high resolution, like everybody wants to go sub-meter for the most part, whereas our field of view, we want as much of a swath of the sky as we can see for clouds, and that's going to be about, I think with our new camera configuration, about 3,000 kilometers by 3,000 kilometers swaths that we'll be getting. And from there, it's really about the two satellites taking images from different directions. And then when we stitch those images together to make them one image, it's really about our algorithms and processing from there that deliver our numerical data as well as the nice 3D pictures that we can develop.
You mentioned those two satellites. So how do you synchronize them? Is this something that is like satellite to satellite communication, or you desynchronization from the ground station that makes those satellites in sync when they are taking pictures?
Yeah, so actually the satellites, luckily, because formation flying is difficult, so if we were not flying in formation, there can be elasticity between the satellites themselves. We expect they'll be about 500 to 300 kilometers apart at any given time. But it's really when the image is taken in the exact position of the satellite, it's very dependent on the star trackers and the ADACs that are in the satellite itself for the pointing accuracy. When we get those from each satellite and the image, that's how we coordinate what was taken when at what exact position, and then that's where we stitch them together from there.
What was the biggest challenge from technical perspective that you had to solve in order to make the whole thing operational?
Ooh, there's so many. I think the biggest one was taking imagery from a moving platform, initially the space station, of moving features at high speeds was extremely difficult. And then figuring out the way to precisely get the positioning and the time stamp, and then to be able to take one image and then the next image and then put those together. So that was maybe the one of the largest technical challenges was that movement, but also the algorithms were, of course, extremely difficult to develop and took, I would say, about 20 years that those algorithms have been developed and refined, and then the validation coming from that 5 years over the space station mission. And that was definitely the hardest part was that. So at least all of our homework is done. That's why we're pretty excited that once we're in orbit, we're not commissioning a new sensor, we're not commissioning new technology. We're basically just doing what we had done before, and the satellites won't take months to commission. We'll have usable data in just a matter of weeks once we have our satellites up.
That was my guess that the time synchronization might be one of the biggest challenges, especially when you mention the concept that you want to connect data from various stations, like the on ground and from space. So in that case, the exact precision of location and timestamp is crucial because based on that data, you can calculate the movement of the hurricane and hopefully predict the way it will go. AI is a huge topic lately, and you said that you've got those algorithms figured out. Do you plan to leverage AI in a way to make better predictions, or this is not ready to be used for this specific application?
AI is really interesting to us. We know that we'll be layering a little bit of AI on some of our processing. That's already baked into that. However, where AI is going now for weather forecasting is extremely interesting, but also a little bit limited. We're hearing a lot about AI being used for weather forecasting and improving forecasts, but for the most part, to train the AI, you need historical data. And what we know now, especially if you talk to meteorologists, they kind of talk about the before times and now the new normal. And the new normal is anything but normal. We're seeing things that we've never seen before, unfortunately. Climate events that have broken records, whether it's warming oceans, storms that we just don't see that we hadn't seen in the past. Rapid intensification is one event with hurricanes that we're seeing it more frequently because of warmer temperatures and overall, AI is not trained to look for these things. In the coming years, our data will actually help improve AI as we'll be feeding more into that. So AI is going to definitely change weather forecasting. It already is, but what we need is to collect more data, especially as these events are becoming more frequent and less predictable with climate change. We'll be able to actually train AI a little bit better in the coming years as we start to take observations of these events and start feeding the models a little bit better.
Could you give us some success stories of Tropical Weather Analytics? You said that you are in the market for quite some time. So, what are the main goals that you achieved?
Well, the commercialization aspect is relatively new. I will say about 4 years that we've been able to develop the technology to a point where we could actually commercialize it. I'd say the biggest success is over the years, even getting to the point to develop the measuring technology to the point that we could actually validate it on the space station was one of the biggest successes. Actually keeping and getting funding for all of these contracts along the way. This is about $200 million put into this from various ways. Over 110 million directly to our previous company, Visidyne, but then from there, the space station mission was probably about another $40 million. And prior to that, the Project Ramos, before it was cut off, was about $60 million, maybe even 80 million. We count for inflation in today's dollars. So I think the biggest success is that we've managed to persevere through a lot of ups and downs and actually improve the technology, and that we're here is maybe the biggest success at all. And it's the biggest will be once we're in orbit and actually providing better hurricane forecasts and providing better weather forecast overall. That'll be the biggest success that we're looking forward to. But getting here was the challenge and a big success.
You just listed a huge investment in terms of capital that was needed to get when we are right now. So what about the business applications? Do you see any potential of return of investment from those huge amounts of money in terms of pure business applications apart from the forecasting to save people's lives?
Yeah, absolutely. So even 24 hours notice can actually reduce damage and cost by about 30% per extreme weather event. Any hurricane that's usually over $1 billion if it's a hurricane, if it makes landfalls, it can be even 100 billion. So right off the bat, we know we can save 15% of cost just by providing a better hurricane forecast to municipalities and states or countries that are impacted by them. But other than that, there's a lot of commercial applications because there is not a business on the planet that is not impacted by weather. We just kind of take it for granted because there's nothing you can do about weather. But you can make weather work for you and actually get an edge in many areas if you have an earlier and more accurate forecast, and especially reliability. So this can come from agricultural output. You can grow more crops on less land if you have a more accurate forecast and when to deploy resources. Aviation, especially, will be a key industry for us. We can save about 2% per flight on fuel cost if you use our 3D wind data and just integrate that into your flight scheduling models. Maritime would be another one where 80% of ship optimization is not about the ship or engineering that you can do. It's actually about weather. And obviously, there's not many weather radar stations in the open oceans. We know we can help maritime save time on their trips and optimize the ships a little bit better, most likely save on fuel cost as well. So those are three areas that we're really interested in helping. Obviously, insurance will be a big one. Even offshore oil rigs have to shut down sometimes for weather that actually does not impact them or reduce production. So we know that if we're providing them with a better forecast, that they can save on downtime. Or conversely, if the storm is actually going to impact them, they can do things to make sure that it doesn't have the rig go completely offline. So there's a lot of commercial applications for our weather, and commercial weather is a growing industry. I think it's about $7 billion now. Expected to grow to about 25 billion in the next few years. The more that climate change is having an impact, the more that commercial weather will actually be needed for businesses, for sustainability efforts, as well as just to not get wiped out, just to make sure that their business model is okay. Whoever has the best weather forecast is going to be able to provide a lot of commercial applications across quite a range of industries.
Being sailor myself, I totally understand the value of knowing the winds on the ocean. Even for cargo ships, as you said, the wind might impact the fuel consumption, which is significant cost of its own. So you said that currently you use cameras, but take us to the future. Do you plan to develop some new sensors to increase accuracy of predictions, or you'd rather improve the algorithms themselves because the data that you gather from cameras is good enough?
There will be an evolution of our space hardware as well. So the first generation of satellites will be daytime for the most part. That's the expectation. And then they only measure when we have cloud coverage. So that's two drawbacks: is that we don't have nighttime and we don't have clear air wind measurements. We will want to improve those, and the only way we're going to be able to do that is with advanced sensors. So we know that there will be an IR payload later on so that we can do nighttime. That'll be in generation 2 of our satellites. And then hopefully as well in generation 2, we start to develop a hyperspectral payload. And this hyperspectral payload should allow us to get clear air wind. Our goal is a 24/7 wind and cloud modeling across the entire globe with the number of satellites, and then these 2 additional sensor payloads, which will be an IR and then a hyperspec. And luckily for us, somebody kind of did the work for us when it comes to using the hyperspec to measure wind. So it's really about refining how we use that sensor data and apply our algorithms to that. So there's still a lot of science to be done, certainly, to marry up what we do now with these new types of sensors that we'll be using in the future generation of Hurricane Hunter aircraft. But it'll be an evolution, and we will need those 2 additional sensors down the road.
What is the best way to contact you if someone got an idea about business application that could leverage data that you provide?
Well, they could certainly go to our website, and that's weathersats.com, or they could look up Dan Harkins or Tropical Weather Analytics Inc. On LinkedIn. We're always there, ever present on LinkedIn for sure. So that's where we get our information for the most part from the meteorology community as well as the space community for what's going on. So that's where they can find us, is weathersats.com or on LinkedIn.
Thank you so much, Dan, for taking time to meet with us today and to speak about this extremely important topic that can help people to predict and somehow cope with the extreme weather events. So thank you so much, and I wish all the best for your journey. Hopefully you will even go farther of what you got right now.
Well, thank you very much, and I really appreciate the invitation, and we love talking about this, so I really appreciate coming on and having a second. So thank you.
Thank you for listening. Go to thefingers.com to find more materials about the Internet of Things domain. My name is Łukasz Malinowski, the Internet of Things advisor and trainer.